So the key agendas are, when does a loss function really fail very quietly behind the scene? That is something we need to know. And which kind of models can get impacted because of this kind of a failure, very quiet, silent failure? And how can we have them fixed? Okay, so this is going back to the classical machine learning space where we're going to be exploring it. So let us say we have written a classifier, a very standard, simple classifier like a decision tree classifier. This kind of code we usually have. The data is the training data. So first line declares the classifier, second one is fitting the classifier, so it's trained, and we are making some prediction. All right. Usually it never stops here. What we usually do is we go to the next step, and at various points in time on this trained classifier, we will be running this line of code, predict prabha, right? And we use this predict prabha in various places to understand how good our model's actually assessment is for a given test set. All right. So this is a very common thing, which is why the predict prabha is even being placed, and it is being used in production systems. Now, we want to kind of look into this predict prabha's reliability. That is kind of what we are going to be talking about in this session. So let's rewind back and really understand what kind of a loss function these systems behind the scene are running. And we know they are running a log loss function, which is entropy based. All right. So here we do see that we have a binary cross entropy based log loss function, which has two elements to it. One is this yi, which is basically going with a log of the probability of the yi. And the same way 1 minus yi is going with log of 1 minus probability of yi. Here the probabilities predicted for that yi are actually factored in as we compute the loss. Now what this means is, if there is an incorrect probability coming out of this, for whatever the reason is, we are going to explore that reason in a minute, then fundamentally this output is wrong, and we are going to silently face this situation. Okay. All right. So when log loss fails quietly, when would it fail? Let's understand, talking about failure of log loss. When can it usually fail? Number one, it fails when the class distribution is imbalanced. Okay. It is worth seeing this equation. That's why I put it in a binary cross entropy format. So the only two things are there: A class, B class. And if A class is more dominant, then obviously the system is skewed towards A class. And it has been observed that that is one of the reasons when log loss actually starts failing quietly. Class is imbalanced. The second place where it starts to fail is when the models actually do not return true probabilistic estimate. So this is a space where we are talking now about the model dependency, the kind of model we chose, and that it is not going to give me the true probability or the estimate of the probability. And that may be a bit intriguing, and that's where we are going to explore a little bit more, which is about the model. So we're going to talk about that in a minute. But now let's look at the third reason why log loss fails quietly, is that the outsample distribution diverges from the training distribution. Yeah, this may sound like, yes, that is true. That is something that we see all the time when the test set is far more diverged than a training set. So we've never seen that kind of a skewness or kurtosis or certain behaviors in that test set. Then it's going to be off the training set, and in those cases, log loss does fail. And maybe this third one is a place where we all have seen many, many different reasons why overfitting, underfitting happens, and that we have tried generalizing the model. Okay. So this may be the most obvious one, but these two are the subtle ones with which the failure really happens. And one thing we're going to explore today a lot in detail is the second one, which is the models that don't return the true probability, because this is where the core of the problem is. Why I say that is because a lot of times we know class distribution is imbalanced. Then what do? We work on kind of correcting that imbalance, or surrounding that data. We try to collect more data, or maybe generate more data and try to get a little bit more balanced. Okay, so we thus know there are some methods with which imbalance could be addressed. We also know that there are methods with which some generalization can be done. And both these two I cover a little bit more when we talk about how to set up validation pipelines in a subsequent session. And today's session, we'll focus more on how do we get to know the models that are not returning true probability, and how do we fix them? Okay. All right. So here, let's just quickly see. For the class distribution imbalance, we're either stuck with oversampling, methods to resolve it, oversample, undersample, or run some sort of a smooth. Now, having seen this in production, I would not recommend you guys do any of this very aggressively, because none of the good smooth methods, even though they are technically correct, are giving good out of sample production efficiencies. Okay, so take them with a pinch of salt. Don't do them aggressively. Do them moderately, and get your own probabilities calculated. That's one thing. And the second one is the place where we're going to spend a lot of time, where the predict proba is actually not an assurance of the true empirical probability, and we're going to see those models where it does fail. Okay. All right. So then comes the question: what does it mean as true probability? Okay. The answer is real simple. The probability of our target class distribution as seen in the data. That is the most important thing. So I have a training data set, and that is all is entirely seen by our models. So if the model can give me the accurate probability distribution, the probability estimate for the data that is seen, then we have no problem. Then we call that as the true probability. But when it doesn't do that, we have a problem. Okay. So it kind of like, again, makes us ask the question, why would the models not do it? Correct. So we have to drill this a little bit more in detail. But before that, let us assess which are the models that are not guaranteeing to give the true probability. So here I've chosen the word guarantee, and you will yourself be able to assess why it is not guaranteed. All right. The first is our favorite decision tree and its variance. So decision tree is not guaranteed to give you true probability. How do we prove this? So take this example. Take a decision tree classifier, like the simple code that I showed you earlier. Compute the predict proba. Keep the values on one side. Next, go in there, change the decision tree's hyperparameters like max depth, max leaf nodes, min sample leaves. Fit the model, and now try and bring the results of a predict proba. The answers will not converge, or usually don't converge. Okay, so that is a quick way for you to validate that the resulting probabilities will change based on the tree's growth, which are driven by these hyperparameters. Yeah, I want you guys now to visualize how the tree growth is actually constrained or is liberal when these parameters are being used, for you to kind of like be able to again visualize how the predict proba is going to vary. Okay, very good. And also, obviously, we need to know that when the tree is completely unrestricted, totally I have no restriction on any of the hyperparameters, then yes, your tree's predict proba will converge to the true empirical probability as seen in the data. Because the tree has to be drawn fully till the last possible node it can have for the given data, which is literally a complete fit or the overfit, as we call them. And in those cases, yes, the predicted probability is matching the empirical probability. Okay. So a subtle point, but it's an important thing. Now that we know what's happening with the decision tree and its hyperparameters, let's also be clear that other models like support vectors, random forest, XGBoost, CatBoost, LightGBM, you name it, all these bagging boosting models based out of the decision tree usually fall in the same trap, because they have some of these parameters that are driving the models, either the tree generation in case of these models, or surface generation in case of a support vector. Okay. In support vector, we have the gamma parameters that basically drive how the surfaces can tilt and shift. And also we have the nonlinear fit functions, right? So we have functions that are nonlinear to which we project at a higher dimension for us to be able to do the linear classifier. So because of that underlying nature of those functions, yes, you have the chance that it is not giving you the actual probability. Okay. So keep that in mind, that these models that are really our favorites to solve many of the problems are prone to have this problem, that they are not going to give the true probability. Then the question is, how are we going to fix it? Okay. What we have to do is, in some way, we have our model prepared, however it is, let's say with a decision tree with certain constrained hyperparameters on the tree growth. And then after that, we have to align those predicted probabilities to the true probabilities. How can we align it? The best way to align it is align those predicted probabilities with the training data. All right. If we can do that alignment, then automatically the result is the predicted probability will get shifted and more closer they move towards the true empirical probability. All right. So for us to align the predicted probability and get our target distribution, we are going to be talking of a few solutions available in sklearn. Okay. We can use a calibration classifier cross-validation class, calibration class classifier CV, to achieve some of this for us. Okay. So what it does is it basically provides a model. It's basically a two-stage model it provides you, which is applied to the results of an existing model. So let's say I have some results from an XGBoost model. Then it does take my results from the XGBoost model, then modify it with another model to make sure that you're aligned to your genuine, true empirical distribution. Okay. So it does it in two stages. One is it takes the existing results, updates the predicted probability of your model, makes them closer and closer to the ground truth probability. So that is the gist of what the calibration classifier CV is doing. Okay. When we do this calibration classifier CV, obviously for it to do this updating of your existing XGBoost results, it is going to be using some other model. And what is that some other model? There are two options available. One is it can either use a logistic regression to bring that shift, or it can use an isotonic regression to do the shift. Okay. So these two in their isolation may not be as powerful as XGBoost, but these two in their isolation are true, are models that give you true probabilities for a given empirical data. Okay. So therefore, when we use the XGBoost results and kind of adjust with these, then you're moving your predicted probability more closer to the true probability. Okay. And obviously, in these cases, calibration classifier CV, we obviously have to use a strong cross-validation strategy to avoid overfitting into our data. And why we say that is because there are two models inherently dependent. One is the XGBoost itself, and the second one is obviously either it's logistic regression or isotonic regression. So we can choose which one we want depending on our needs. And using strong cross-validation means we should have a very good validation pipeline. And in fact, I have 2 sessions scheduled to talk about validation pipelines for you guys, which we should definitely focus on. Very good. So let's look at some samples. So let's say I have a data with about 10 classes, 200K size with about 100 features. Okay. We choose a model with addition tree where we have a max depth restricted to 10. And we are going to be choosing the logistic regression with a C equal to 1. So fundamentally, the penalty of the logistic regression is neutral, meaning it does penalize because it's 1, but it is neither extreme nor too low. Okay. And my cross-validation CV is at 5. Okay. This kind of a code snippet you might have to write. Fundamentally, the first one is my classifier. The second one is, these two are my classifiers that are basically taking in this decision tree and then making the adjustment in the predicted probability and giving me newer classifiers. Then this sort of a plot could occur for you. Okay. What this means is you're basically, look at this way. When you have a perfectly calibrated system for your given data, this is kind of the line, the idealistic line that you're going to be running with. However, if you see where decision tree is at any point in time, it would be like this. Okay. So it is basically going through this. And it's kind of far off genuinely the predicted probability that it should be from the true empirical observations that it is. And why that happens is fundamentally because of the decision tree's depth parameter, or it could be other hyperparameters that are restricting the tree growth. And in such cases, having us applied the isotonic and the sigmoid based, meaning logistic regression based calibrated classifier, which is shown here. DT plus sigmoid is shown here, which is this line. This yellow line gets shifted much more closer to the ideal via the blue line. So that's kind of what is shown in the blue line, where the probabilities are much more shifted. Though there is a little bit of caveat, there are some points in time where it is far away. There's nothing we could do about it. There are sometimes the price is there whenever we do this shifting. But usually what has been observed is these probabilities are much closer to the true genuine probabilities after you put them through calibrated classifier CV. Okay. So let's also look at the chart. Let's also look at the mean predicted probabilities across the board. For my data, if my mean predicted probabilities are like this, as is plotted by the logistic regression, this is kind of what is coming out of my decision tree, primarily because of the depth of the tree. Okay. Maybe if the depth of the tree was a little bit more constrained, I have a doubt that some of this would get filled. But right now, it does look that it is really focused on the extremes. So when you have obviously DT plus sigmoid done, then there is more density out here, which is kind of reflecting almost the densities that are seen by the logistic regression in this particular case. And when we do this, obviously, like I showed you in this earlier chart, there is some cost to it. There is some, it doesn't come free for us. There are some data points around which we are going to have a deviation. But what we are essentially saying is for a majority of things, this alignment is close to the true self. Okay? That's what it says. All right. So what is the cost other than some deviation? We see from a loss perspective, there would be some cost in that. So let us see this. If I have fitted a logistic classifier, then for now, I want you guys to focus on the precision and recall and also this Brea loss. Brea loss is kind of like a normalized loss. It's much easier for us humans to read than the log loss from standardization perspective. So that's about 11%. I get that loss. And then my precision recalls are about 84%. Okay. In addition tree model, which has been constrained, then I do get a Brea loss a little bit more. And I'm getting somewhere like 84, 85%, about the same effect. So in this particular case, DT with that parameter is not adding so much value genuinely. Okay. And when I put this DT plus sigmoid as part of my correction, then I do get a little better loss, Brea loss compared to a DT only. But what I have essentially paid the price is the precision. Okay. I've gained in recall because now I have a little bit more of that history if you want to think that way from a recall perspective. I have that. However, the precision of my classifier has gone down. So that is the cost that we are going to be paying. And this is why only tracking with F1 score is sometimes very blinding. We should use this as a generic measure to add some value rather than make a lot of decisions out of pure F1. So it is better to assess these precision and recalls independently and understand where the cost is. So in this particular case, the cost is my precision for the benefit I got in my recall, and that I reduce my Brea loss. Okay. So that's kind of how this overall alignment of probabilities to the true empirical data really works. All right.